Hi everyone, it's me Prabodh again. Today I'm into a problem of elastostatics. I think you remember during my last video tutorial, that means in the video of heat transfer, I have talked in detail about creating a part, material, section, assigning section, and how to do heat transfer analysis, right? Today I'm just demonstrating one problem on plane strain. So it's again a 2D problem, but not on heat transfer, but on elastostatics. So by elastostatics, we mean we're doing static analysis and we're using the elastic properties of our material, right? Before proceeding here, I suggest you to watch that video on heat transfer in case any confusion arises while creating a part, defining the material properties, and assigning the section and running the analysis. So if you need any suggestions or any, you have to resolve your any confusion, just go there. I think I'll not be talking in much detail today about Abaqus basics, but I'll be demonstrating the problem on elastostatics, so I might be going like a bit quicker than I did my last tutorial. So let's start with our problem on elastostatics for today. So this is our problem. It's a 2D plane strain problem. Look here, it's not a plane stress, it's a plane strain problem. So you'll know in detail while I'll be demonstrating in Abaqus CA. So it's a problem of 2D element. So it's rectangular element. It's of length 10 inch, height 8 inch. So it's also a boundary value problem. So it has got boundaries on its two adjacent walls. So fixed supports are assigned here. Horizontal and vertical displacement on fixed supports are 0. So we'll be assigning that boundary condition. Our material is steel. So we'll be using this elastic modulus value of 29,000 per square inches, and our Poisson's ratio will be 0.333. So it's again a wall with unit thickness. So we're doing our dimensions in inches and gives for loading. So unit thickness means a 1 inch wall. So again, for a recap, it's a 2D element which has boundary conditions assigned on its two adjacent edges. So they are fixed supports. So it's a 10 by 8 inch rectangular wall. Material is steel, unit thickness wall. So, and the loading conditions are horizontal load of 5 kg and vertical load of 10 kg, right? So now I want to proceed to Abaqus. So here's Abaqus. So first what we have to create is part. So I'm just creating part, name wall. So it's 2D planar, deformable, cell, and unit thickness, like we did previously for a transfer problem, right? So continue. So you'll be taken here to this huge space with grid lines. So I'm not doing today with the help of coordinates. I'm just using another tool that is easier for if you have just one element. So I'm just creating a rectangle randomly. So it's a rectangle. I can assign dimension from here, this tool. So here you can see it's 8 dimension tool. So I can add the dimension from here. So we have this dimension to be 10 inches, right? So it's changing to 10 inches, and our vertical dimension is 8 inch, right? So okay, done. Now we have created a wall of a rectangular plan of 10 by 8 inch, right? So there's a part. Now what material we're using? We have to create a material definition. So we're using a steel. So steel. So last time we did for thermal stuff, but now as we're doing elastic problems, so I'm just using the elasticity, which is on mechanical part. Elasticity, elastic. So you can assign the Young modulus here. So what's the value of Young modulus? You can see is 29,000 kips per square inches and Poisson's ratio of 0.333, right? So Young's modulus 29,000. So I'll always be telling be consistent while using the units in Abaqus, right? So we're using here inch for length and kips for load. So it's 29,000 kips per square inch. So we don't have to change anything. So it's our consistent unit system. And Poisson's ratio, since it's unitless, we can assign 0.333 directly, right? So it's still with following two properties. Okay, so we have successfully created a material still. Now what we have to do is we have to create a section, right? So section, so it's, let's say it's a wall section. So don't worry here, because whatever you assign here, you can modify your parameter later. So I'm just using solid and homogeneous wall here. Continue. So material is still everything I'm leaving is default. So okay, so we have now created our wall section, right? Then the next step is assigning that section to our part wall. So here, wall, parts, wall, and section assignment. So select the regions to be assigned a section. I'm selecting the region, this one, done. So it has already got wall in it. So wall section, we're assigning that section into our part, right? So we have successfully assigned the section as well. We do not have to worry about anything here because we're just doing a simple kind of problem. If you have to do any complex problem, then you might have to use all these parameters here. So now I've created a part wall and assigned our section made up of steel, right? Now the next step is creating an assembly. So instance, we have just one part, so we're just selecting wall, and here we are making it independent so that we can mesh later, right? So I'm just clicking OK. So we have already created our instance wall, right? Now the next thing what we have to do is creating a step where we can do our elastic problem, right? So step, I'm creating a new step, name Elastostatics, and here, since it's an static procedure, so we're selecting the static generally and continue, right? So we don't have to do anything with nonlinear geometry, so we're leaving default off. We don't have to worry about this right now because we're just doing a simple problem, not a complex one. So okay, this test, right? Now after creating a step, what we have to do is we have to assign a boundary condition, right? So we have got two boundary conditions. I mean the boundary condition in two of the edges, so we're assigning the boundary condition, let's say fixed support, right? So we're assigning boundary condition on displacement and rotation. So continue. So select the regions. So we're selecting this one and this one as our two regions. We're selecting done. So what are the boundary conditions? So displacement on x and y is 0, right? So displacement ux and ui are zeros, right? Okay, so 1 denotes to x-axis and 2 denotes to y-axis, right? So just u1 is 0, u2 is 0. Just these two are boundary conditions. So I'm selecting boundary condition on these two edges. Okay, now we have assigned the boundary condition, right? Now the another one, another thing what we have to do is assigning these loads, right? So we're sorry, I'm sorry, went on wrong tab. So okay, we have to assign the load, right? So load, let's say p load. What is the type of load we have to assign? It's a point load, one vertical load of 10 kips and one horizontal load of 5 kips, right? So these are two concentrated push, concentrated load. So continue. So where are we putting our loads? On this end, right? So select, done. So here look. So what's the values? It's horizontal 5, vertical 10, right? In kips. So kips is our unit system, so we don't have to convert to any other unit system. So we can use directly the value 5 and 10, and both are positive 5 and positive 10. So positive 5 on x, positive 10 on y. So positive 5 on x, x means 1, right? Positive 5. Y means 2, positive 10, right? So 1 CF1, 1 concentrated force on one direction means x direction concentrated force, and 2 means y direction. And this is the point, right? So, okay. So we have now successfully applied our load, right? So look here. So we have applied the boundary conditions. We have assigned the dimensions, rectangular 10 by 8 inch, 2D cell element. We have assigned wall. We have assigned the elasticity and Poisson's ratio. Now what is remaining is number of elements. So we're doing 4 element system, right? Similar as the previous one. Okay. So you might remember what we have to do is we have to go to mesh and we have to select the element type. So we have to assign the region, select, done. So everything you have to put here is default. The only thing you have to change, I don't know what will be here doing your default, but now I'm changing it to plane strain, right? Since we are doing plane strain problem. So plane strain. Okay, done. Now what we have to do is assign the seed, right? So seed, select the edges. We're selecting all the 4 edges so that we can assign 4 elements on this part. So done. So we are assigning local seed by number. So we're assigning the 2, right? So if we put this number 2, then 2 edges will be this edge, and it will also do partition 2. So it will be 2 on horizontal and 2 on vertical. Then it will be 4 elements in total, right? So apply. Okay. And look here. Okay. Now what we have to do is mesh the part. So you're saying okay to mesh the part instance. So as because we have already done our everything. So okay. Now we have successfully created our 4 part elements, right? Our 4 element part, whatever you can say. So it's a wall, it's converted into 4 element, and we are running our analysis now. So we have done everything. We have assigned part, mesh, load, material, dimensions, and boundary conditions. And we have also assigned elastostatics in our step, right? This is step. Okay. Now the job, create a job. Let's say elastostat. Continue. I'm just using here multiple processor because I'm running this from my CPU. So okay, and right click, submit the job, and it's submitted. Look here, it's submitted. Now it's changing to running, so it will run for a few seconds and will be completed. Yeah, now it's saying completed, right? Then click right, look for the results, and you'll see one ODB file. So this file is for result, and you can look at the deform shape. So originally it was this rectangle. Now because you applied 10 kips load on vertical direction and 5 kips load on horizontal direction, then your wall, let's say 2D element, is deformed this way, right? So you can look here. So from this figure, what you can guess is your part is deformed to some extent. Let's say if you are analyzing this point, right? So this point is deformed to some extent on vertical direction. So it's saying positive, right? So it's getting bigger. So it's going positive. This is your initial, right? This is your initial. So y coordinate is changing to positive. So this part is increasing. Deformation is positive in y direction, right? And in x direction it was this way, and I think it has changed slightly to left, right? So it might be negative, but can look here. So right, primary, so u is your deflection, and you are now concerned with x and y direction, right? So one means x, so let's say x. So x, this point blue, right? So this is the blue point. So x point is deformed negatively, as we could have guessed earlier, right? So it's negative 2.69 times 10 to the power minus 5. So it's an inch because you have selected your unit system to be inch by selecting your dimension in inches and selecting your elastic modulus to be in kips per square inches, right? So it's deformed negative. This point is deformed negative by this one, right? However, your centroid is deforming positive, right? Or you can just look from here. It is here, right? This part. Look at this part. This is changing, yeah, positive, right, and up. Okay. Okay. So this is your deformation contour in x direction. So what in case of y? So look at y. So this point red, so it's positive, and it's 1.2 10 to the power negative of 3 inches positive, right? Okay, look here. This point, this is deformation on y-axis, so it's sending up. That's why it's showing plus. You can just guess from a deformed shape only as well, right? Look here, this part is deformed, positive in y and a little bit negative in x. If you look at the centroid, what you can say is positive in y and positive in x as well, right? You can just look from here. Both positive, right? Up and right, this part. You can see from contour as well. So in y, still positive, right? Yeah, look this one. And in X is red, so it's still positive. So positive in red, X and Y. So this is how you can interpret your analysis. And the next thing what you can do is from here you can just create your plot by selecting this create XY data. So you can choose here. For now I'm choosing my field output, so I'm choosing stress components, I'm choosing meshes, so and I'm choosing, let's say I'm choosing for central, yeah, okay, I'm choosing for this part, right? So you can plot here, so it's plotting stress versus time, right? So you can look from here, you can plot this way. From this you can just change or format your plot, format the line, format the style, format your axis, right? Okay, so from here you can look in your animation version. So like after the application upload, it changes this way. First it was this way, after changing, right? So you can see originally it was this, and after applying the load it was this. We can look from here, right? Okay, so this is all what I have for you today. I think I will be uploading one video on Elastostatics problem, or let's say just static analysis for a complete frame system. This one and the previous tutorial was just on 2D elements. You do not have to worry about orientation, and you do not have to worry about the connection. But now I'll be doing one tutorial on how to analyze complete frame system. So it will be consisting of multiple parts, let's say beam and column, and it will be consisting of the orientation of beam and column and connection between the beam and column and boundary condition, and what's your preference on analysis, whether you will be doing 3D analysis or 2D analysis. You will learn much more on the tutorials, so please watch out for that. I already told that I will provide the link for my previous video in this one, so please look at the link after the end of this video. And if you have any confusion regarding this one and previous video, I'll always tell, just email me on prthehall1@gmail.com or prthehall1@go.olemiss.edu. You can email me on any of these two email addresses, then I'll try to respond as quicker as I can. Okay, so that's all for today. Please stay safe and best of luck on learning Abaqus. Thank you.